So the title is Locally Cartesian Closed Infinity Categories. So to be precise, there should be one here, infinity one categories, but just as we say just category for one category, I think we can also say just infinity category for infinity one category. So the intuition is that locally Cartesian closed one categories are, in a certain sense, semantics for extensional Martin-Löf type theory. So this is the Seeley correspondence, and it's not completely precise, but I think it can be made precise by some tricks. So I put just one question mark, and that's not to question Seeley, it's just to so now the idea is that locally Cartesian closed infinity categories should be intentional. And here I put two questions mark. Because in addition to the same problems that there were already in the one case, there are several further problems. And inside here we could have intentional Martin-Löf type theory with a univalent universe. And this should be infinity toposes.
Can I interrupt for a second? So by infinity you mean like infinity 1?
Yes, I had a 1 here and I erased it before you came.
Oh, sorry.
I think there are no more questions mark here than there are here. So
Yeah, I think there is.
Yeah.
We don't know that the univalent universe exactly corresponds to object classification. It looks the same.
it looks the
There's
same,
no
yes.
Modulo of other stuff, there's no proof yet. So.
But in any case, since I know so vanishing little about type theory, I will just talk about this. So this is just as motivation. So the important thing is that infinity toposes are characterized inside the locally Cartesian closed infinity categories as those that you can say it in various ways. One is to say that it satisfies descent. And the other way is that it has a map classifier. So I will talk about this. And the map classifier is a univalent universe. As much.
Or an hierarchy of those, right?
I'm sorry?
Or an hierarchy of those.
Yes, so I should put for each
For each size.
regular cardinal, yes.
For each size.
Yes.
Maybe size can be internalized though.
There's some small generation condition.
Yeah, okay. So I should also say that what is over here is really small, I think. Whereas what I know something about is only the presentable version of all this. I mean, presentable locally Cartesian closed infinity categories. And I don't know how much of this is really essential or if it's just for convenience. So, for example, well, now I'm already starting to talk instead of giving my talk. So you need presentability for controlling many things and just work without thinking too much. But I think that many of these arguments can be done in a small locally Cartesian closed infinity categories if you're just very careful with what you do. But I put here presentable. And of course that's so this is locally Cartesian closed infinity category with descent or a map classifier. And this is presentable. So this we saw very clearly an example of in Guillaume's talk yesterday. He exploited univalence to prove a case of descent, namely that you can construct a map over a colimit by taking the colimit of the pieces, and then by descent that will be what you want, namely there's some pullbacks. I will come to all this. Okay. So maybe I should start with the size stuff, because then I can get it done and don't have to come back to that. Okay, so a simplicial set S is kappa filtered. Kappa is a regular cardinal. If for any kappa small simplicial set K and a map into S, there exists an extension to, you put a cone point. And then a Cabot filtered colimit is a colimit over a Kappa filtered diagram. And an object in a infinity category is Kappa compact when the representable functor into infinity groupoids commutes with Kappa filtered colimits. And then a category is Kappa accessible when it is locally small. So that means that all the mapping spaces are small, and the Kappa compact objects form a small, essentially small subcategory. If I say category, I should put infinity category, but I just forget it. Which generates C under Kappa filtered colimits. So I should assume first of all that it has Kappa filtered colimits. That has. So this is just as it is for one categories, and the standard example is the category of sets, and it's generated by finite sets. So the omega compact objects are the finite sets. And every set is a omega filtered colimit of finite sets.
When you say commutes, do you mean up to how much of these?
Yes. And then presentable means kappa accessible for some kappa and small colimits. And I will only work with presentable categories.
Excuse me, may I interrupt again? How can, which generates C under K filtered colimit? So in your example of sets, it would mean that sets are generated by finite sets under finitely filtered colimits. What does it mean, finitely filtered colimit?
So should I put a bigger cardinal, or is it open?
The ordinary notion of filtered colimit.
And every object is the colimit of its finite power set, of all inclusions of finite sets into it.
The diagram, I don't know if it's the point, but let me observe that the diagram, when you express a set as a directed union of finite subsets, the diagram is of course not countable, but the full set
It's
is
this one.
filtered in the sense that given two finite subsets, there is a third one, in fact a union, which dominate, and in this sense is finitely filtered, because any two, any is dominated, but the whole diagram is big.
And
I don't know if it's the
infinitely
point.
filtered, what does it mean?
I'm sorry?
What does it mean, for example, countably filtered?
That would mean that any countable family of subset of elements is dominated by one. The cone, that's the cone.
Yeah.
condition.
So it's not this one that's omega small or anything, but that it has this property with respect to omega small things.
So if K is countable, then we will be able to dominate.
Yes.
I don't know if it answers.
Yeah.
So I just want to put this to be precise, but I will not use it very much. I will just yes, okay. So there's another characterization of presentable, and it is that it is a accessible localization of a pre-sheaf category. So that means that the pre-sheaf category P, then there's a localization functor like this, where the inclusion, which is the right adjoint here, preserves kappa filtered colimit for some kappa. So all this presentation business is technically very convenient because you can play with all these localizations. So let me start with topuses now. I'm going a little bit backwards, but I think I should start with topuses. So one topos, well, since we are in the presentable case, one topos is Grothendieck topos. So usually we say that that's a category of sheaves on some category C with a Grothendieck topology. So this means that it sits inside the category of pre-sheaves, and that there's a sheafification functor, A sheaf. And this sheafification functor is left exact. So this is the classical picture. In infinity topo theory, you can take, at least Lurie does, take this as the definition. So you define an infinity topos is a left exact localization of a pre-sheaf topos, a pre-sheaf category.
Would you say pre-stack?
Well, so I just mean functors from some into infinity groupoids. And here you should actually put accessible.
And you don't want to write pre-stack?
No.
Because you wrote it pre-stack.
No, this is a H. This is a pre-sheaf.
Okay.
So the idea from this viewpoint is that you start with the infinity category of groupoids, and maybe that's the most interesting of your infinity categories. And then you gradually look what we can do in here, where else can we do that? And the most general that we would like to do it is maybe in presentable infinity categories. But inside here we have first pre-sheaf toposes, and then we have infinity toposes, and then we have locally Cartesian closed infinity categories, and then the most general are the presentable categories. So here I should also put presentable. So these are localized, they're just arbitrary accessible localizations. Here they're the left exact accessible localizations, and I will also tell you what these are as a localization. Yes.
Maybe this is what you're about to do. Would you be able to spell out what localization means?
Yes. So it's a left adjoint whose right adjoint is fully faithful. So localization is a left adjoint L with fully faithful right adjoint. So we think of the fully faithful right adjoint as an inclusion. So it will typically look like this. There's typically a pre-sheaf category. Then you have the localization, and it will be regarded as a subcategory of P. You can think of this as a reflection into a subcategory. Okay, now I will start here.
By infinity groupoid, you always mean here concomplexes, is that right? That's the only definition you've given us so far.
Yes, that's one model, so to speak.
That's the only model you've told us about so far, right?
Yes, yes. And when I say infinity category, I mean quasi-category, because it's the only model I have talked about.
There's a certain sense in which the choice of concomplexes doesn't matter, right? Because everything that you're saying is invariant under equivalence of infinity categories.
Yes. So my convention that I explained Monday is I say infinity categories for the abstract thing. And then one choice for realizing this is quasi-categories. But the interesting theorems, of course, are those that are invariant under homotopy, so you can transport them to complete Siegel spaces or simplicial categories and so on. Okay, so now locally Cartesian closed infinity categories. Or presentable locally Cartesian closed infinity categories. It actually follows from this that C has small limits. In particular, it has pullbacks. So if I have a morphism from x to y, then I get a pair of adjoint functors like this. I should maybe just put so one way to say locally Cartesian closed categories is that the pullback functor has both adjoints and they correspond to sigma types, substitution, and pi types. So now Monday I talked about adjunctions in this very abstract way of putting up a bifibration. I just want to show you how simple this particular adjunction is. So you can look at the category of arrows and the codomain vibration down to C. Then to have an arrow in C, that's the same thing as having this. And you pull back this to here. Now, since C has pullbacks, so this is always a co-Cartesian vibration. And since C has pullbacks, it's also a up vibration. And this property pulls back to here, so this one is also both Cartesian and co-Cartesian. And by the definition I gave of adjoint, that means that this bifibration represents an adjunction. And it's precisely this one. Because what is it? It means that I have 0 in here, and I have 1 in here. Here I have the total space of the adjunction. And if I restrict to the 0 simplex, I get this slice. And if I restrict to the other one, I get the slice over y. And this one is now the left adjoint coming from here to here. So I get. So that comes from the up Cartesian property of this one, and I get the other one here. That's because this is also a vibration. So Cartesian lifts of this gives me this, and Cartesian up Cartesian lifts gives this. Okay, now there are several definitions of what locally Cartesian closed is. Locally Cartesian closed infinity cat when satisfies any of the following equivalent conditions. So one is that colimits are universal. Maybe I write them down and then I explain each of the points. 2 is that all these pullback functors have right adjoints. Three is that all the slices are Cartesian closed. So all are Cartesian closed. And 4 is the characterization in terms of localizations. So C is a locally Cartesian localization of a preheaf category. So let me start to explain these conditions. So one means that whenever you have, well, let me stick to that morphism up there. If I have A is some colimit in Y, then I pull it back and I still get a colimit. So I pull back the whole diagram along the map, and what I get is a new colimit.
You don't assume that colimits exist, do you?
That's part of being presentable. It has all colimits.
Oh, I see, okay.
And that's exactly what allows me to so there's nothing to explain here. This one has right adjoints, but under the assumption that C is presentable, these two conditions are clearly equivalent, because the adjoint functor theorem says that if a functor between presentable categories preserve colimits, then it is a left adjoint. So this one is adjoint functor theorem.
Can I interrupt you again?
Yes?
Your very first correspondence where it says ceiling, but there you don't assume any colimits.
No. So
So like a typical Martin-Left type theory would not generate any.
so I should be a little bit more
Okay.
cautious.
That was easy.
So I said that I think most of this can be done also for small categories, but technically it's more complicated. So this one would not be true in the small setting, but the other one, of course, would always be true, because if F has a right adjoint, then it preserves whatever colimits might exist. So 3 means that, so there's a functor from here to here that takes an object A and makes the product with some B. So this is inside the slice. So this product is actually, if you think of this sitting over X, then this is this. So the product is the product in the slice is the pullback in the base category. So being Cartesian closed means that this has a right adjoint, which would be Z maps to, and you put Z to the B. So this is just notation for this right adjoint. So if you have 2, so that this one has right adjoint, then you easily get this one, because you just compose with, what do? You do like this. Maybe I change the X and the Y.
A cross X or something.
X to A to X.
Sorry. Let me see if this works. So this one is you take the pullback. Okay, so you take the pullback and you compose. So it's a upper star followed by a lower star. And
X to 8 to X.
this is X,
Yes.
and this is yeah, A. Okay.
Oh, right, okay.
But in any case, you realize that it's a composite of two left adjoints. So therefore, you get this one. It is then, in that case, F upper star, F lower star.
I'm sorry, just a very small point. You want to exponentiate by A or by B?
By B.
By B, then we should go into C over B, I guess.
Okay, so this should be FBS. Thanks. So F is here now. Yes. The other direction is not completely trivial. It's just in one category theory is sometimes called Freyd's lemma, and you can also do it for infinity categories. This one is of a different nature, and I will just say what it means. So left exact means that it preserves small limits. Now, just by having the fully faithful right adjoint, it's automatic that it preserves the terminal object. So it says that it preserves pullbacks. Now, the locally Cartesian localization condition is not to preserve all pullbacks, but only some pullbacks. So L is locally Cartesian when it preserves pullbacks between local objects. So local objects, I just mean objects in C. So this means that if you have a pullback diagram like this, where these two objects are in the small category, and you apply L to that, you get well, I should put L here, but L doesn't do anything to the local objects.
Again, questions of terminology. It may be a little bit clearer if you say base change between local objects.
I actually usually do, so that's I agree.
Oh, okay.
Yes.
Because the pullback is so ambiguous, right?
Yes, yes.
Can look horizontally or vertically if you don't know exactly.
Yeah.
You could also say it preserves pullbacks of maps in C.
Pullbacks
Pullbacks
along
of
the maps
into local objects.
along or along?
Pullbacks of
Along,
maps
yes.
of
Along.
Yes.
maps in category C.
Base change along, yeah, well, preserve base, I don't know. Okay.
Base change along objects then.
Along local objects.
Along or along morphisms in C, because C is as was rightly noted.
Yes.
Because C is a full subcategory.
It's a full subcategory, right. Okay.
This has also been studied classically, where it's called semi-left exact. Semi-left exact.
Semi,
Yes.
exact. What
Yes.
an horrible name.
But it only makes sense when you also have a right exact. I mean, when you have this inclusion, right?
Yes.
When you have the capital.
I don't want to establish this equivalence because it's a little bit technical, but I want to come back to it later because it fits into this scheme of realizing these categories as different kinds of localizations.
semi-insufficient?
Yes.
And this is true for infinity, yeah.
For presentable
Any
infinity categories.
Is the equivalence between, say, 2 and 4 require presentability?
I mean, to be
Or, sorry, what I mean is, if I start with the locally Cartesian closed infinity category, and I have a locally Cartesian localization of that, concluding that the localization is, again, locally Cartesian closed. Is that
that's okay. Yes. Yes.
I see. It doesn't have to be appreciative category. It can be
Oh, so there's in establishing this number 4, there's a lemma saying that a locally Cartesian localization of a locally Cartesian closed category is locally Cartesian, and that does not use presentability. Okay, so now I will move towards the topos axioms. And the first thing I will do is to rewrite this condition in a, at first sight, strange way, but it will, well, maybe it's not strange since we had this talk yesterday, so. So 1 prime. Suppose we have a Cartesian natural transformation between 2 diagrams, U and F. To C. And we have an extension to the cone, so F bar and U bar and alpha bar. Then colimits being universal means that if you pull back, so if alpha bar is Cartesian and U bar, the colimit diagram, is a colimiting cone, then F bar is a colimiting cocone.
Can you remind us what it means for a natural transformation to be Cartesian?
It means that on all the naturality squares are Cartesian. So this says that, so
this is a sophisticated way of saying that.
yeah, it's deliberately a little bit strange, but because now I will use this to go to descent.
Okay.
But let's see how it goes. So if U is a colimit diagram, then we can take the value, the component of alpha bar on the cone point. So we have alpha bar on the cone point. That will now go from the colimit of U bar into F bar of the cone point. And since the whole diagram is Cartesian, it means that F is the pullback of U. And what it says is that it's again a colimit. In other words, it's the same thing as saying that colimits are universal. I mean, there's too much data here. I could just put U, and I pull it back, and I say it's a colimit cocone again.
Can you spell it out a little bit more? Sorry, I didn't get it, and I don't know if everybody else did.
Okay, so I just started with more data, and I put more conditions. All the data that is needed is that you have U, which is a colimit cocone, and you have the component here. From that, you can construct the rest because it's Cartesian. Oh, yes, sorry. Sorry about that. That helps. Okay. Now it's... Thank you.
And I think you need f bar of delta 0 and colimit of u.
So this should be the component of the diagram at the cone point.
So it's f bar of delta 0
bar.
is u bar.
F bar.
And u bar of delta 0 is
Colimit
the
of
colimit
u.
of u, not of u bar.
Okay.
There we go. Good.
Thank you. Thank you.
Yeah, let's think about that now.
Would you mind drawing a little picture?
A picture. I will draw a picture. Just 1 second, but I will just state the converse of this condition, and then I will draw pictures.
Okay, I can wait.
Okay. The reason I wrote in this strange way is that the descent condition it's just the opposite implication. It says that if alpha is Cartesian and if u is colimiting, well, both are colimiting, then alpha bar is Cartesian. Is that the opposite? Okay, if I put some of the conditions up here globally. Colimiting. Okay, so now I have...
Does it say in the second line? Does it say u bar co-limiting? I think you have that down here.
So I assume globally that u bar is colimiting,
Okay.
and that alpha is Cartesian.
Okay.
Then alpha bar can be Cartesian, and so now this is a global condition. So alpha bar Cartesian implies that f bar is colimiting, and the opposite says that if f bar is colimiting, then alpha bar is Cartesian. Okay, this is Reszke's descent condition, and I will now draw an example.
You will draw a picture?
Yes, and I will draw the same picture as Guillaume did yesterday. So the condition says that suppose you have an object which is assembled from local data, like this. So I put k is this, and k with a cone point is this. So here is my colimit diagram over this. That's u.
That's u bar?
Well, the whole thing is u bar.
Ah, okay.
And now I give myself alpha Cartesian. That means that I have some local objects here. Alpha is Cartesian. That means that these local data agree on the overlap. F is this F. It's so F is only on K. So that's the local objects that I want to glue.
You want to push out these things.
So in the descent condition, you're not assuming all the data on the left given. You're saying you've got alpha and f bar with those conditions, and then then there exists u bar and alpha bar to make alpha bar.
U bar is also assumed to be colimiting.
But so there exists alpha bar not given alpha bar it must be Cartesian, but there is an alpha bar that's Cartesian.
Yes, yes. I apologize. This is not clear. I think I also assume that I have alpha bar.
In the second case, alpha bar is uniquely
Actually,
determined by the development condition.
actually what you start with is alpha bar. I mean, alpha is reduced from alpha bar.
Alpha is a restriction of alpha bar.
Because
Yes.
it's a restriction.
Yes.
So you have a cone and a natural transformation between two diagrams on that cone.
Yes.
And you're supposing that the base of the,
Mm,
that you, this one.
It's Cartesian.
You're writing U, sorry, I'm really very formal here. You're writing U there as the colimit of U, and I don't like that.
U or U bar?
You should,
Yeah. Okay. I see your point.
you just give us a different notation for the colimit or something.
Yes.
And I would be happy. But U what?
U on the cone point.
Make it a bit, my sight is very fast. Okay.
So this is the cone point. Well, maybe I should call it infinity.
It's a colimit.
The cone, the vertex.
The vertex. Okay, I go back to this.
Okay.
Okay. Now we come back to
Explain it on this diagram and then we can come back.
yes. So now I'll do what Guillaume did yesterday.
Yes, okay.
Just a second. The Z condition is on what? It's a condition on what?
It's a condition on this.
On a pair which consists of what? Of two.
Of two cocone,
Two cone diagrams.
yes, and
then
natural
a
transformation between them.
And so there is the same condition on such a gadget. Two
Yes,
cone
yes,
diagrams and
yes.
a transformation between them.
Yes.
Okay.
And in the end, I want to impose this condition on all diagrams.
On all triples like this. you mean?
Yes.
Could you complete the diagram by adding F?
Yes. Let me do this because this is what Guillaume did yesterday,
Okay.
and I apologize for the confusion.
No, it's okay.
So what Guillaume did was he wanted to construct something over U, and he had the local data, and it agrees on overlap. So all this amounts to saying that we have
You're going too quickly. You're supposing that U is a colimit, is a push-up.
yes, that's
And you already have F bar. So there is already some F delta 0 there.
no, I don't have F bar. I only
You have F bar.
Yes.
okay. I didn't mean to have it. Let me do the example, and then maybe we can discuss how I should have said it.
Okay.
Because what Guillaume did was right. So you have this push-out diagram, and you have local data, and you want to construct something over U.
Yes.
What do? You take the push-out here. And then you cross your fingers and hope that it works. And what does it mean that it works?
Yeah.
Well, in any case, you have a map here because of the universal property. You have a map. So works means that these two are pullbacks because you want this one to agree with its local parts. So that's saying that the whole thing is Cartesian, not just alpha, but also the extension is Cartesian. Okay.
So how about now drawing it in general? So you have U bar, you have F, and you have alpha between the restriction of between F and the restriction of U bar to K.
Yes.
And the alpha is Cartesian.
Yes.
And then the condition is that there exists an extension. Well, not that it. So what is the condition? Either that there exists an extension to F bar and alpha bar, which is Cartesian, or that the extension of f bar by colimit leads to alpha bar, which is Cartesian.
I think this is the
second
one.
Okay.
Yeah.
The extension of f to f bar by colimit
Yes, no, it looks
has a
like
Cartesian alpha.
Alpha bar.
Yes.
Alpha bar.
it's equivalent,
Yes.
so it works in whatever setting.
Yes.
Yes.
That's pretty tricky, but understand.
Yeah, right.
I'm sorry about that.
No.
But so what you should have in mind is what Guillaume did. Okay? And then the statement is that,
Everybody was here.
no, that's right. So the statement is there is a way to formalize this in general. And I think it's what you said. And it might not be what I wrote.
And that will be a property of C. When you quantify over f and u bar and alpha, it will become a property of C.
Yes. And now,
And that's a fancy way of saying that colimits are universal.
no. Colimits is universal is the opposite implication. So
Okay. Yeah.
this implication is to say that colimits are universal. And the opposite implication is to say that you have descent.
Okay.
So to say that colimit is universal means that if you start with the push out of u and f delta 0, just this vertex.
Yeah. Then you pull everything
you pull
back.
All diagram, you get a push out diagram upstairs.
Yes.
Right.
Yes.
So you just have the corner on the right, f delta 0.
Yes. Then you can lift everything and it will stay a
Then
colimit.
you take the pull back.
Yes.
Colimit diagram.
It would be much easier to write it in code.
I'm sorry?
It would be much easier to write it in code. And that will be no confusion.
You have become cock addicted.
Yeah, I'm sorry about not writing it correctly, but I hope you get the idea. And anybody who really wants, we can sit down and do it correctly. So now the theorem.
Before you skip the theorem, can I ask one more thing?
Yes.
The pullbacks and pushouts here are all weak or infinity or homotopy.
Yes,
pullbacks.
they're the only ones we have. Yes.
So the maps we don't have to care about if they're vibrations or something like that?
No.
Because we're not,
No.
they're just maps and everything's only up to one.
Yes. So Rask's theorem says that presentable locally Cartesian closed infinity category is a infinity topos when it has descent for all.
For all descent data.
Yes. Okay.
So this is like a zero theorem characterizing Grothendieck topos.
Yes, it's very similar.
Except that it's much simpler in some sense.
So Giraud said two things. He said sums are disjoint and groupoid objects are effective. So you can, he didn't say groupoid. He said equivalence relations. But in the infinity case, you have to say groupoid objects, and you prove that it's equivalent to Rask's condition. Okay, I'm running a little bit late, but I want just to give you a very short example of how this fails miserably in the category of sets. And the example is, I have it from Rask. You take as your U this colimit diagram. And then your local data will be this, but with a twist. This should be the involution identity, and this should be identity.
The top is a flip or what?
Yes, on this summand you switch, and here you don't.
That's cool.
And what you see is that if you take this push out, as we did here, and cross our fingers, here you get 1. because these two components cancel, and the colimit in the category of sets is just 1. And this square is not a pullback. So this is Resk's example.
What if I do it in an infinity tuples? I can make the same diagram.
Yes?
What do I get then?
Well, here you get, first of all, something different than 1. You get a circle.
Okay.
And here you also get, what do you get? You get 2 copies of the circle.
It's just one circle.
Ah, it's a double cover. It's a double cover of a circle. Ah, yes. Yes.
One circle?
I mean, it's a double cover of the circle.
Twisted.
Yeah, but
Yes.
it's
Still
the
no
two
circle.
cover.
It's a connected thing. It's this famous
But
trick.
a twisted double cover, not just like this, but a twisted one.
Yes, of course, yes, it's the double, but
Yes.
it's an amazing thing. I really love this idea of X. It was,
So when you look at this, you feel pity for the category of sets.
what did you say?
When you look at this, you feel pity for the category of sets. Okay. I wish I could have done this properly. But now I will move on to the other condition, which is univalence.
If I may steal a couple of seconds, I just wanted
Yes.
to say that for people who were here earlier this term, I gave a couple of talks, and I had 3 boxes, and I only got to the first 2 boxes, and this is the 3rd box.
Oh, great.
Why affinity groupoids are better than sets.
Here, we'll schedule another session for
No.
you, Mike.
So this is it?
Okay, so map classifiers. So in a classical topos, well, you can do the elementary axioms, which includes having a sub-object classifier. What is it? It means that if you have your category C, you can look at sub-objects. So that's a functor into set. It takes a set and it returns the set of sub-objects of X, meaning isoclasses of monos. And this is representable. And it's representable by, so subobject of X is in bijection with Hom from X into omega, and omega is, for the category of sets, just the 2. And as any representing object, it has a universal family, which is the inclusion into one of these 2. So you can also say that there's a bijection between monos and maps from X to this. So the idea is that for any mono, there's a unique way of obtaining it as a pullback from this one. So this is the classifier for all monos.
What are the classes
Yes, yes, yes. Or if you want, you can make the category of all monos with the codomain fibration down to C. And then you only take the Cartesian maps in here, so the pullback squares. And then this is this one is a terminal in this category of monos and pullback squares. And this holds for any topos, but of course you get more complicated classifiers. So now you could ask, can we classify more than monos? Could we classify arbitrary maps? And you can't. If you want to classify maps with 2-element fibers, what would be the terminal? Well, that should be this. This is the candidate for being a terminal 2-cover classifier, but it's not because because you could exactly have different. You could have permutations up here. So it's not unique. It's not terminal. It's weakly terminal, maybe in some sense, but it's not terminal. In set. So the problem is that you have automorphisms. So if you want a classifier for set maps, what you can do is you can go to groupoids. And that's what happened in algebraic geometry in the 60s, that people wanted representing functors to represent functors, and they could not do it with sets and schemes, so they had to go to stacks. They're just the same thing for groupoids. So in the category of groupoids, you can do this. You can just take the groupoid of all sets of a certain size, say, and you can take the groupoid of all pointed sets, and that is classifying fibration for this all groupoid fibrations with discrete fibers. Okay, so you go to one homotopy level higher, and the first place where you can get one for all maps is infinity toposes. So I think this is also due to RESC, but maybe I should put Lurie too. That a presentable locally Cartesian closed infinity category is an infinity topos if and only if. Okay, so now there's a new problem for when you go to infinity toposes, and it's about size. Nobody is afraid of talking about the groupoid of all sets, because automatically when you step one level up, you sort of admit a new universe. But if you want to do it in itself, you get a universe problem. So you need to put a cardinal bound. There exists a classifier for, and I say what it means, relatively kappa compact maps. And this is for all regular cardinals kappa. So what does it mean to be a relative kappa compact? So F, it means that whenever we have a pullback square, then Fs is kappa compact, then X prime is also kappa compact. So you can think it means that the fibers are kappa compact, but it's a little bit more general.
I have the impression that the condition that is locally Cartesian closed maybe is not necessary.
That's what Mike said also. But I tried yesterday to figure it out, but I could not.
Okay.
But in the case of one-toposes, there's something like that, but that you get exponentials for free if you just have the subobject classifier. I mean, there's some trickery that you can get many things for free, but
Power objects. You need all power objects. Not
you
just
need
the
power.
And then from that you can get colimits for free. Not exponentials, colimits for free, right?
Since locally Cartesian closed infinity presentable, well, presentable colimits are there because it's presentable.
I'm eager to hear about this. If
Colimits is more complicated, right? So I can get colimits from subobject classifier
Oh,
and locally Cartesianly closed.
oh, I see. You could, I see.
There is some very, very non-trivial way of doing it.
Okay, it's a bit like in an elementary topos.
Yes.
It's not obvious that colimits exist. Or maybe in homothetic theory that inductive types are there, or something like that. I don't know.
The construction, the classical construction in elementary topos of colimits from the subobject classifier and the locally
Cartesianly closed.
relies. Yeah. Relies, I think, to some extent on kind of the impredicativity of prop. On the thing. So
well, anyway, personally, I'm mostly interested in locally Cartesian closed categories, so I never thought about it. Okay, now I come to univalence.
Where did you find the object classifier on the backboard? It was classified for.
Well, I started write down something, but I maybe object classifier.
Yeah. Is it here on the backboard?
No.
It's almost there. Is that classifier for? Is that the object classifier?
Write down the definition of classifier.
Relative.
Yes. I'll do that now.
It's a terminal object.
So to do this, I will just introduce some terminology. So I follow Lurie's notation. So this is the category of arrows, and this is the codomain vibration down to C. Now, if F is a class of maps, stable under pullback or under base change, then write superscript F for the full subcategory whose arrows belong to F. So objects are in F, and we also need the Cartesian part. These are the same objects, so identity on objects, but only the Cartesian arrows for these for this vibration. So P Cartesian arrows. So that just means pullback squares. So if I just say pullback squares, I'm talking about the one simplices in here, but this is more a global way to say it. Okay, this is a Cartesian vibration, And when you restrict to the Cartesian arrows, you get a right fibration. And this I talked about Monday. Otherwise, it's just the infinity version of being a fibration in groupoids. And now what? Okay, so since it's a right fibration, it has associated a presheaf. But this presheaf might have big values.
Naively, this is this OCF is the category whose objects are arrows
Yes.
in F,
Yes.
and whose morphisms are Hilbert squared.
Yes. Yes.
Okay.
So right fibrations correspond to presheafs by Lurie straightening, but it might have big values. So that's what the hat means. So F is called a local class when this associated thing preserves limits. So this condition is designed to make this presentable. So in general, a presheaf which preserves limits is presentable if it takes small values. So if f takes small values, this implies f representable. So this means we have to bound the fibers of this map. So this you can do again by a cardinal. So if kappa is a regular cardinal, it should be big. This is something technical I don't really understand. Then f kappa inside F is again local. And now it's bounded, sorry, I should say this is kappa, relatively kappa compact maps in F. So this is also a local class, and it also preserves all limits, and now it has small values, so this one is representable. And that's going to be the classifier for maps in this class. So the representing object and its universal family is classifier for F kappa. So I can rewrite this as the class all kappa is local. Well, no, no. I can just say that the class of all maps is local. That is what. Why did I? Over here. This is just a reformulation of what I said before, that the class of all maps is local. So that if I restrict to the kappa compact ones, there is a classifier. So this is a reformulation of Resk-Lurie.
If I may interpret, the functor F, which you constructed, has a category of elements like an A presheaf functor.
Yes.
And this category of elements is precisely OCF.
Yes.
So that's the connection between this category and F.
Yes.
It happens that you start with this category and you say, oh, I have F then, but okay.
Yes.
And to say that F is representable exactly means that the category of elements has a terminal object.
Exactly. Yes.
Yes, which is the condition.
Yes. Okay. Now univalence.
Will you explain the theorem? What are the conditions and what is in the left-hand side of the equivalence, the upper part of the equivalence? Is the whole thing for a presentable locally continuous closed infinity category, or what is it that's equivalent? Yeah.
I'm so bad at logic.
This is not logic, this is just careful.
Yes. No. But before I could not figure out what were the.
So it's the descent condition that you're saying is equivalent to the existence of the classifier.
Yes.
Because that was the additional.
Okay. So
Yeah.
this is the same.
Yeah, that part's the same. Okay. So it's descent that is equivalent. to
So
this classifier.
descent is equivalent to having classifiers. So now I start with any map. Then I can form the sheaf of equivalences. Well, not sheaf, it's a right vibration. Of equivalences of P. So this is over here, who is fiber over a point F, G is the space of equivalences over T of the pullbacks of the original map. Okay, so this one you can, if you want, define formally as sitting in this fiber sequence. This is not the whole slice category, it's only the equivalences in here. And down here you have two copies. And here you just have, you put that pair. So this is defined from this fiber sequence. Now what I'm saying now is the infinity category version of the univalence axiom. You also have the, so this is of equivalences. You also have the right vibration of identities. And it's just the representable one given by the diagonal. So this is the object, and as a right vibration it's this. Maybe I could put it like this. And if you want to spell out the right vibration in terms as a sheaf, then it's C which takes an F, G and map it to map S, F, G. It's just the representable functor by delta.
I'm confused. Why do you have right vibration there and not just somehow vibration? Where is the right coming?
I mean, it's this functor. It's just because I want to map it into this one. So to put them on the same footing.
I see.
I mean,
Okay,
this is just the functor represented by this, if you want.
okay. Do you want to describe the vibrations over S cross S, not over C cross? The map representing the equivalence, or will you do that, or no?
Let me do, I will, there's a canonical map from this one into this one. So to give this map, this is represented by the diagonal. So to give this is to give an object in, and then you apply this to the diagonal. And that's here. So egg P applied to the diagonal, and that's equivalence is over S of identity pullback of X and identity pullback of X. And in here we have the morphism. So giving this object here is to give this one here. And the definition is that P is univalent when U is an equivalence. Do you agree with this?
Yes, I think I would try to make it internally, but then I think it's a little, maybe a little non-trivial to define what is EQ of P. I mean, internally I would just consider an object.
Yeah.
Okay, so you would first represent this.
Yes.
You would first represent this and then say that it's the same as the representing object for this. Now
I would represent that and then say that the morphism from S to this representing object is internally an equivalence.
okay, so instead of working with these right vibrations, you work directly with the objects.
Yes.
Okay, but the only way I know to prove that this is representable is going through here. So I don't.
Well, if you have a locally Cartesian closed situation, this is like an internal Hom, but only with the invertible pairs.
Okay.
It's a subobject in the internal Hom. In the local internal
Yes,
Hom
right.
over S, from X to X.
Maybe over S cross S.
Yeah.
Over S cross S.
You have to put a copy.
Right.
I'm running out of time, but I just want to write two equivalent characterizations of this, and then so P univalent so if you have so here I write all maps, but the parenthesis means that it's only the Cartesian squares. So this takes a map F and apply it, pull back this one, pull back P. And this should be mono. And it's also equivalent to saying that the class FP is bounded local. So bounded local means that it's a terminal object in, so this one you could write as it's just the image of this map.
When you say that something is mono, you mean what exactly?
I mean -1 truncated.
Between categories, so what do you mean by that?
On the left-hand side, you have the category object in C over S. That's the point.
Yes.
And you want to say that this functor is mono.
Yes. Maybe I should say fully faithful.
Just face.
Fully faithful, but restricted to ISO. I mean, in other words, it's not the.
Well, yeah.
It's the category of isomorphism in C over S.
Yes.
I mean, all objects over C over S, but only isomorphism between. Let's say from T to T prime, you only consider invertible maps.
Yes.
From
In any case, I can write exactly what I mean for this to work. I mean that a map is mono if this is a pullback. That's what needed.
a functor
Yes.
is mono,
Yes.
and this is a pullback.
Yes.
And you mean, and here is this still strict pullback or weak pullback, pseudo pullback?
This is a weak pullback.
Yeah, all must be weak here.
Yes, everything is weak.
So
Does this agree with what you said?
I'm sorry.
Does this condition match what you said about the
I
isos?
have to think about it. I don't know. Maybe. Okay. In infinity one categories, you put back in infinity one categories.
Yes. In the infinity category of infinity categories. Okay, but just to finish, so univalence for type theory, that should be imposed on the universe. So that means that the class of all maps should be local. And this is the topos condition, the descent condition.
You've added bounded local here. The boundedness refers to the condition here for each kappa. The class of kappa ones is representable.
Well, I mean, if you have your universe, it's a vibration, so it corresponds to P somehow. And this P, there will be a bound. You just take a kappa bigger than the size of any fiber.
I don't understand what it means to say that it's bounded local. What is the definition of bounded?
So bounded is that its corresponding presheaf is representable. So it means that it has fiber smaller than some kappa. And this kappa could be just kappa bigger than any fiber. So it's sort of tautological that anything that does have a terminal object, it is bounded.
When you put when you made the definition over here of a fibration P being univalent, there's nothing in there that says it classifies some maps. It's just a condition on P itself, right? I mean, it classifies all its pullbacks.
Yes,
But
exactly.
I think the statement is something like that. That for any kind of small subclass of maps, there exists a single map such that any map of this subclass can be obtained by pullback, and the single map itself is univalent.
yeah, that's that. Yeah.
Yes, yes.
So you have to add to really be an equivalence here, you have to add to P being univalent also that P classifies in some weaker sense also univalent, and then you have this equivalence, no?
That I don't understand.
Now, up there, it's just an equivalence between P being univalent and all the maps obtainable from P by pullback satisfying some condition.
Okay.
But then in general, one has to say that there exists something from which everything can be obtained by pullback,
Yeah,
and
that's
it's
univalent.
univalent.
Okay, got it.
So this equivalence is starting from P, but one could alternatively do what you're saying if one wanted to start from a class of maps.
If you start with a class of maps, then first you need to impose the cardinal bound and then find the representing object, and that is your univalent fibration.
I mean, since sort of the universal map determines the family, okay? Here there's a conditions on univalence.
Yes.
For the map.
Yes.
You could also describe these conditions for a family. That's what you're doing in some sense.
Well, I mean, in a sense, that's maybe this condition. I mean, this one, when you say it's mono, that's...
Could you describe it without referring to P? Just suppose that you have a family stable on the pullback, and you want to say that this family is univalent.
I don't know in general, but in a topos,
No, the descent condition is about the existence of P.
Yeah, but that's what you're asking for.
But P may exist without being univalent.
But the point is presumably that it will exist and exist in the sense which is required by the descent condition, which is a very strong sense, that automatically implies univalence. I guess that's what I mean.
Because P is just sitting as a terminal object in a certain family of Cartesian square or something.
But terminal in a homotypic theoretic sense.
Yes,
Yes.
I agree.
And descent, yes, the descent gives the stronger than just representability. And descent gives the existence of P, but it also gives more, and it seems that it gives enough to make P univalent.
Okay, so
I mean, one, if you are in a topo, so you know that for sufficiently for a fixed kappa, you do have a fibration. Then you can characterize